Welcome to Introduction to Manufacturing. Today we'll be covering ceramics, which is the second topic out of three topic series on metal, ceramics, and polymers. How is ceramic defined? It's an inorganic compound that consists of a metal or a semi-metal and has one or more nonmetals. So let me give examples of two that we could discuss. Silica, which is silicon dioxide, is a main ingredient in most glass products. That's called that's considered ceramic. Alumina is aluminum oxide, which is used in various applications from abrasives to artificial bones. And they have more complex compounds such as hydrous aluminum silicate, which is a main ingredient in many clay products. So, what are the properties of ceramic materials? They have high hardness, they have great electrical and thermal insulation, chemical stability, and high melting temperature. However, when it comes to ceramics, they tend to be brittle and they virtually have no ductility. That can cause a lot of problems during the manufacturing process and the performance of ceramic products. Now, some ceramics are translucent in that the window glass, like window glass, which is based on silica, is one of the best examples. Now, looking at other ceramic products, for clay construction products, you may have seen bricks, clay pipe, and building tile. Refractory ceramics are capable of high temperature applications, just such as furnace walls, crucibles, and molds. We also have cement, which are used in concrete and they're used for construction and road. And then finally, we have whiteware products like pottery, stoneware, fine china, porcelain, and other tableware based on mixture of clay and other minerals. Proceeding on, you have glass, like bottles, glasses, lenses, window pane, glass fibers like thermal insulating wool, reinforced plastics, and fiber optics, abrasives like aluminum oxide and silicon carbide in grinding wheels, cutting tool materials like tungsten carbide, aluminum oxide, and cubic boron nitride. And they have ceramic insulators like electrical transmission components, spark plugs, integrated chip substrates, magnetic ceramics, and computer memories. There are examples and prime examples of magnetic ceramics. Bioceramics, and they're using artificial teeth and bone. And then here you can see some of the examples for each of those. The strength properties of ceramics. So theoretically, the strength of ceramics should be higher than metals because their covalent and ionic bonding types are stronger than metallic bonding. However, metallic bonding, as we discussed before, allows for slip, which is one of the basic mechanisms how metals deform plastically. And the reason they can deform plastically is because you have some slippage mechanisms occurring at the microscale. However, in bonding, bonding ceramics is more rigid and does not permit that slip. So therefore, there's inability to be able to slip. That inability to slip makes it a lot more difficult for ceramics to absorb stress, meaning they become brittle. And here you can see an image of a typical metal versus a ceramic in blue. Now, in reality, this is in theory. In reality, ceramics contain imperfections in their crystals structure, just like in metals. Vacancy displays atoms. You're going to have microscopic cracks. Internal flaws tend to concentrate stresses, especially under a variety of loading conditions. So therefore, ceramic will fail by brittle fracture much more readily than if it was a metal. The strength performance also is less predictable because of these random imperfections in the system and the process variations. These imperfections cause ceramics to behave in an unpredictable manner. Also, can effective strength can be less than a metal. The compressive strength of ceramics has some usefulness. So the frailties that limit the tensile strength of ceramic materials are not nearly so operative when compression stresses are applied. So for example, ceramics tend to be very strong in compression than in tension. As a consequence, in a lot of applications, we have learned how to use these components so we can load them in compression rather than tension or bending. And here are some examples of arches where the loading condition introduces a compression state rather than tension state. So, what are the physical properties of ceramics compared to other materials? You have the density, and the density for most ceramics is lighter than metals, but heavier than polymers. The melting temperature is higher than for most metals, so that's an advantage for high temperature applications. Some ceramics decompose rather than melt. So they may not melt, they will decompose. Electrical and thermal conductivity is lower than for metals, but the range of value is so great you can use them for a lot of different applications. So some ceramics are insulators while other are conductors. So depending upon what you want to use it for, there is an application for it. The thermal expansion is a little bit less than metals, but the effects are a lot more damaging because it's brittle material compared to metal. There's three basic categories of ceramics. Traditional ceramics, clay products such as pottery, bricks, common abrasives, and cement. Glasses are based primarily on silica and distinguished by their non-crystalline structure and may be considered a traditional ceramic. You also have new ceramics. More recently developed ceramics are based on oxides, carbides, and they tend to have better properties, mechanical and physical, than traditional ceramics are based on mineral silicates, silica, and mineral oxides found in nature. The primary products are fired clay, cement, natural abrasives such as alumina, and then also products and processes to make them date many years back. So this is not a new thing that we're suddenly using. Glass is also silicate ceramic material and is sometimes included among a lot of traditional ceramics. Raw materials for traditional ceramics, there's quite a bit of it. Let me give you examples of them. So, mineral silicates, such as clays of various compositions, and silica, such as quartz, you may have heard of quartz, are amongst the most abundant substances that are available in the nature and constitute a principal raw material for a lot of traditional ceramics. Another raw material for traditional ceramics is alumina. So these solid crystalline compounds have been formed and mixed in the earth for over billions of years by complex geological processes, but offer advantages in the manufacturing of ceramic based systems. Now, this is ceramics looking at a glass as a state of matter as well as a type of ceramic. As a state of matter, glass refers to amorphous structure of a solid material. The glassy state occurs when insufficient time is allowed during cooling from the molten state to form a crystalline structure. So here in this curve, you can see that you have amorphous structure. It can be brought up with temperature to be a super cool liquid. So there's a transition between amorphous structure, which is in this case non-crystalline structure of solid material, and it can be transformed as you move up here in this curve to super cool liquid and then liquid. So the glassy state occurs when there's insufficient time during the cooling, and a type of ceramic glass is an inorganic non-metallic compound that cools to a rigid condition without crystallizing. If a glass material is crystallized, it is a glass ceramic. Glass is a type of ceramic. So why there's so much SiO2 in glass? Because SiO2 is the best glass former. The main components are 50 to 75% in glass products. It naturally transforms into glassy state upon cooling from a liquid, and whereas most ceramics crystallize upon solidification, so that's a benefit that these glasses have. There's other ingredients listed here that act as a flux during heating, fluidity in molten glass for processing, improves the chemical resistance against attack by acids, and adds color and alters the index of refraction for optics. Glass ceramics. So a ceramic material is produced by conversion of glass into a polycrystalline structure through heat treatment. Now, the proportion of crystalline phase change can be from 90% to 98%, and the grain size significantly smaller than the conventional ceramics, which makes glass ceramics much stronger than the glasses from which they're derived. So yeah, glass ceramics has an advantage due to their polycrystalline structure through heat treat. What is the advantage of glass ceramics? They have efficiencies in the processing into that glassy state. You can get to better dimensional control at the end over the final shape. It has great mechanical and physical properties like high strength, there's absence of porosity, so therefore there's low thermal expansion as a consequence, high resistance to thermal shock, and that's why you'll see that a lot in cooking ware and heat exchangers and some radomes. Now let's look at silica. It's a quartz-based system, crystalline silica. Fused quartz or silica, we call it amorphous silica. Even just quartz for a type of kitchen countertop. So you may have seen this. Glass is a state of matter, amorphous solid material. Glass is also a type of material. Soda lime glass, which is made by melting silica, soda, and lime. And the most prevalent type of glass typically used for windows and bottles. We also, so I want to point this out because silica is used in a lot of different contexts. And so you want to make sure we have an understanding of that. Also, we have to be clear about the delineation and differences between silicone, and silica. So very important there. There's a little note for now. So moving to new ceramics. Ceramic materials are developed synthetically over the last several decades and they made improvements in the process techniques and also being able to develop greater control of the properties that you get. New ceramics are based on compounds other than variations of aluminum silicate, which form most of the traditional ceramic materials. New ceramics are usually simpler chemically than other traditional ceramics, oxide, carbides, nitrides, borides. So looking at oxide ceramics is one of the most important ceramics used. Although it's a traditional ceramic, aluminum also is produced synthetically in this case. So through controlling the particle size and impurities in the processing methods and blending with small amounts of other ceramic ingredients, you can improve the strength and toughness substantially compared to the natural counterpart. Aluminum also has good hot hardness, low thermal conductivity, and good corrosion resistance. And so here you can see some components. They're aluminum ceramic components. Now looking at carbide ceramics, you have silicon carbide, tungsten carbide, titanium carbide, tantalum carbide, and chromium carbide. The production methods for silicon carbide were developed a century ago. And so these methods are generally included among traditional ceramics. Now, tungsten carbide and titanium carbide and tantalum carbide, these are valued because they're of their hardness and their wear resistance in many applications. So that's why you see them a lot in cutting tools. And so these three must be combined with a metallic binder, such as cobalt or nickel, to be able to come up with a useful product. Otherwise, it will be challenging. Now, looking at nitride ceramics, important nitride ceramics are silicon nitride, boron nitride, and titanium nitride. Properties include hard, brittle, high melting temperatures, usually electrically insulating, and titanium nitride is an exception. Applications include silicon nitride, for example, that's using components for gas turbines, rocket engines, and melting crucibles. But also you may see them in ball bearings. Boron nitride and titanium nitride can also be used in cutting tools, materials, and coatings. So these nitride ceramics and silicon nitrides are excellent because they're hard, brittle, high melting temperatures, and they're electrical insulating. And that's why you'll see them in a lot of high performance applications. So let's talk about some of the elements related to ceramics. You have two alternate forms of engineering and commercial importance. You have graphite and diamond, and you have silicon and boron. Carbon, silicon, and boron are not ceramic materials, but compete for applications with ceramics because they have important applications of their own. And so here I'm drawing a circle over the area that we're talking about here, this transition zone that we talk about in the periodic table. So again, two alternative forms of engineering commercial importance will be graphite and diamond. Carbon derivatives here, very important, and your silicon and boron. And while these three are not ceramic materials, they can compete for those same applications. So therefore, as a consequence, I want to then talk about graphite is a form of carbon with a very high content of crystalline carbon in the form of layers. It's going to look like this. The bonding between atoms in layers is covalent and strong, but parallel layers are bonded to each other by weak van der Waals forces. Therefore, one layer can slip against each other. The structure makes graphite anisotropic, and the properties can vary significantly with the direction. As a powder, it can be lubricant, but in traditional solid form, it is refractory. So it has great temperature applications. As a fiber, it is a high strength structural material. So graphite has significant amount of value. You can see a pencil can be used here because each layer can detach from the next layer. And then in a temperature application, you can be able to take high temperatures, and then as a fiber, it can be a great reinforcement in a composite structure. Now, graphene is one atom layer sheet of carbon. Graphene is one atom thick sheet of carbon arranged differently from graphene. Diamond is a carbon with cubic crystalline structure with covalent bonding between the atoms, and that's what's causing the high hardness. The application includes cutting tools, grinding wheels for machining, brittle and abrasive materials. You also have synthetic diamonds that date back in the 1950s, and the way they do that, they'll fabricate it by heating graphite to around 3,000 degrees C on the very high pressures. Yeah, diamond, you're going to see a lot for cutting tools in manufacturing processes. And then you have silicon, which is a semi-metallic element in the same periodic table that we've been discussing. You can see it right there in the same group as carbon. One of the most abundant elements in Earth, comprising 26% by weight, occurs naturally only as a chemical compound in rock, sand, clay, and soil, either as silicon dioxide or more complex silicate compounds. Properties: it can be hard, brittle, lightweight, chemically inactive at room temperature, and classified as a semiconductor. The guide to processing ceramics is that the processing of ceramics can be divided into two basic categories. Molten ceramics, major category is a major category of molten ceramics is glass working. The guide to processing ceramics can be divided into two basic categories. Molten ceramics, which are major category of molten ceramics, that's glass working, and particulate ceramics, which are traditional and new ceramics. With that said, I want to thank you so much for your attention. We'll pick it up again with polymers. You have a beautiful rest of the day. Thank you all.